Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our last session, we have discussed about the activation functions and the loss functions in detail, the various types of activation and loss functions. And today, in this session, we will discuss about the optimization of machine learning models. What exactly optimization means, what are the algorithms that we use for optimization of machine learning models. So that is the topic of discussion for today's session. So in the contents, we have the most important algorithm of optimization, which is called as the gradient descent algorithm. So we will discuss in detail what is this gradient descent algorithm in today's session. Now, to start with, before I go into what is gradient descent algorithm, we'll try to understand what exactly optimization algorithms do in neural network. What is the meaning of optimization and what is its significance in neural networks? So, to start with, the process of minimizing or maximizing any mathematical expression is called optimization. Optimizers are algorithms or methods used to change the attributes of the neural network, such as weights and biases, to reduce the losses and to provide the most accurate results possible. So we all know in machine learning, what we try to do is we try our model to predict some result, and we want the prediction to be as close as possible to the true output. Now this optimization or optimizing algorithms, they help the neural network to update the weights and biases in such a way that the output becomes as close as to the ground truth. Okay. Now, we'll come to what is this gradient descent algorithm. So as I told, optimization algorithms in machine learning are mathematical techniques used to adjust models' parameters to minimize errors and improve accuracy. And gradient descent algorithm is heavily applied in deep learning. So it is one of the most used algorithms for optimization in deep learning. Now we will see what exactly is this gradient descent. So we have a cartoon here. If we see at the cartoon, there is a cyclist which is at the top of a hill, and he wants to come down to a point where it is not a hill, means from the top to the bottom he wants to come down. He cannot see the entire landscape, he just sees what is there below his foot, and or he can feel that one, and he wants to come down. Now when we want to descend from the top of a hill, how do you choose the correct path? You can choose various paths, but some of them may take very long time to reach. Some of them you may not be able to reach the the ground of the hill or the base of the hill. So how do you choose the correct path? So the same thing you can think when we are discussing about gradient descent algorithm. How do we think about that one? So gradient descent is a first order iterative minimization method. It iteratively updates parameters to minimize the loss function. So just as I was telling, the cyclist is trying to come down to the base of the hill, and every location while he is coming down, it gives the measure how much he is away from the base of the hill. And if he changes his position iteratively, at one point of time he will come down to the hill. Okay. The same thing we will see in gradient descent. How exactly it is? So as I told, it is a first order iterative minimization method. Now what exactly we are minimizing here? We are minimizing the loss function, which is nothing but it returns the error between the predicted outcome and the actual outcome. Okay. So that is the loss or error of any algorithm, of any model, and we are trying to minimize this loss in an iterative way. Okay. And while trying to do this, we use gradients or derivatives to decide the direction of change. Means in which direction should I move so that I come down to the base of the hill without spending too much of time. So that is done in gradient descent algorithm also using gradients or derivatives. It computes partial derivatives of the loss function with respect to every weight in the neural network using the chain rule of calculus. Now, these are all textbook definitions. We will now try to see what exactly step by step, what is a derivative, what is a gradient, what is partial derivative, and how these are used to update the weights and biases in a neural network, which finally affects the loss function, that is to reduce the loss function. Okay. So, we will see how this entire process is done using gradients, derivatives and partial derivatives. Okay. Now, we are talking about or we will be talking about parameters in a neural network. When we talk about updating any parameter in a neural network, we mainly talk about the weights and biases, because those are the parameters which have an effect on the loss function. Now, we will just look into, as I told, one by one we will look into what is a derivative, what is a partial derivative, what is a gradient, and then we will proceed to understand what is the gradient descent algorithm. Now, suppose we have a loss function L, which is a function of the weight, and it is given by 3w square. The derivative if we take, that is derivative of L with respect to the weight w is equal to 6w. Now, suppose my loss function L is a function of weight and bias w and b, and it is given by 3w square plus b square something. Okay. Then the partial derivative, what do we mean by partial derivative? Partial derivative means when there is a function, suppose here L, which is a function of two parameters w and b in this case, then we take the derivative of L with respect to one of the parameters, keeping the other constant. That we call as partial derivative. Okay. So, if we take the partial derivative of L with respect to w, then we get 6w. Okay. Similarly, if we take the partial derivative of L with respect to b, keeping w constant, then we get 2b. Now, what is this gradient? We understood what is normal derivative, partial derivative. Now, we have to understand what is this gradient. Gradient is actually a vector which comprises of the partial derivatives of the function with respect to its parameters, with respect to all the parameters. So, here partial derivative of L with respect to weight w and partial derivative of loss function with respect to the bias. Okay. Both are there, and it comes as a vector, and that is called as the gradient. Now, suppose I have a function with 10 variables. In this case, the number of variables were 2. Suppose we have a function of 10 variables. What will be the dimension of the gradient vector? It will be a 10-dimensional vector. Okay, because we have to take the partial derivative of the function with respect to all the variables that are there. Now, we will see a little bit the intuition what exactly gradient descent algorithm is trying to do. Suppose we have this xyz coordinate and we have weights in one coordinate, bias in another coordinate, and the z axis is your loss function. Okay. And suppose I have this free flying surface which is a loss or error surface. Now, my aim of using this gradient descent algorithm is to minimize the loss function. That means I need to change the weights and biases in such a way so that the loss function goes to its minimum value. Okay. Now, we can randomly select next point in the weights and biases plane to reduce the loss, because we don't know which direction. Should I increase the weight? Should I decrease the weight? Should I increase the bias? Should I decrease the bias? I have no idea. So it is just a randomly we are trying to reduce the loss. Okay. Now, if we use gradient descent algorithm, we get a structured way to move in a certain direction which will definitely reduce the loss. Okay. So, gradient descent algorithm actually gives me a structured way to understand in which direction I should move so that my loss gets reduced. Now, we will see how this gradient descent algorithm is working. Okay. So, let theta be a vector of the parameters of the neural network. Now, what are these parameters? As I told, whenever we tell about the parameters of a neural network, we speak about the weights and the biases. Okay. So, let theta be equal to is a vector of parameters of the neural network, that is weights and biases. Okay. Now, we start from a random value of weights and biases and calculate the loss function. So, we have seen in our previous discussions also how to calculate the loss if you know the weights and biases value. Okay. So, from there we take some random values of weights and biases and calculate the loss function. Now, what we need to do? We need to update these weights and biases in an iterative way, so that the new loss function is lesser than the old loss function. That is what we want to do, right? Because at the end we want to reduce or minimize the loss function. Okay, so that our predicted output is almost same as the actual output. Now, let the change in theta be delta theta. So, you have theta, which is a vector of w and b, and you are changing theta in such a way, the change is delta theta, where delta theta is nothing but a change in the weight delta w and change in the biases delta b. So, delta theta also is a vector of the changes in the weights and biases. Now, suppose I draw it in a vector diagram. Suppose this is the direction of my theta and this is the direction of my delta theta. This is the change. Now, if I add them, theta plus delta theta, then we get something using the parallelogram law of vector addition. So, this is the direction where my theta nu will reside. Okay. Now, suppose we all know that for any vector we have direction as well as magnitude. Now, suppose I don't want theta to change by a huge amount. So, my delta theta I don't want to be a drastic change, I want it to be a small amount. So, in that case what can we do? We can multiply this delta theta with a very small value which we call as eta, and in this figure you can see this is my theta's direction. If this is my eta into delta theta, then this is my theta nu. So, what I have done is here previously the original parameters of the network is embedded in theta, which is w and b. Then I try to change the parameters little amount, which is my delta theta, which is once again a vector of delta w and delta b, and then I take a small magnitude of that delta theta by multiplying it with a factor eta and then taking the summation, which is my theta nu. So, my theta nu equal to theta plus eta into delta theta, where theta nu is a function of my new weight and new bias, and theta is a small value. Now, my next question is, in which direction should delta theta be? Okay. Should I go up? Should I go down? Which direction? Means weights can be increased, can be decreased, same for biases. Which direction should I go? Now, suppose my old loss, not suppose, we have already told, the loss function here is L, which is a function of theta, and the new loss function is a function of theta plus eta into delta theta. Okay. Now, just for convenience, let us call this delta theta equal to u. Then the loss function L theta plus eta into delta theta I can write as L of theta plus eta into nu. There is another extra bracket that has come. I have to remove that one from there. Wait. So, just striking it out. Okay. Now, according to Taylor's series, if we have a function like L, which is a function of theta plus eta nu u, that can be written as a series like this, which is equal to your L of theta plus eta into u transpose. What is my u? U is a vector, which is nothing but your delta theta, and inside delta theta what was there? Delta theta was having the components or having the the terms delta w and delta b. Okay. So, u transpose then the gradient of L plus eta square by 2 factorial into u transpose gradient of L, and so on, the series goes on. Now, if we have eta to be a very small value, then eta square, eta cube, these will be extremely small. In that case, what we can do is we can neglect these terms, and what we want to keep as an approximation is L theta plus eta u is equal to L theta plus eta into u transpose into gradient of L theta. Okay. So, u transpose into gradient, this is a vector multiplication, and eta is a small value. Okay. Now, this is my new loss. No, this is my new loss, and what I want, my new loss should be lesser than my old loss, which is my L of theta. So, the condition that needs to be satisfied here is L of theta plus nu u should be less than L theta. Okay. For that one, what should we have here? This term should be negative. Okay. Now, and we want this term to be maximum negative, because if it is maximum negative, then only my new loss function will be much lesser than my previous loss function. Okay. Now, how do we make this term negative? That we have to see. This is the term in question now. Here, eta cannot be negative. Now, why eta cannot be negative? If we go back and look into what exactly my eta was basically nothing but the small change that I was doing in the direction. So, this was my theta's direction, and this was my eta into delta theta. Now, if I make eta negative, the direction will change, which I do not want. Okay. So, this I do not want. So, I cannot make eta to be negative. Then what am I left with? This is a vector multiplication between the transpose and the gradient of L, okay, which is a dot product between two vectors. Okay. Now, this dot product can become maximum negative when the angle between u and gradient of L is equal to 180 degree. So, that is the place where my dot product becomes negative, maximum negative. So, according to gradient descent, if we want to reduce the loss, we should move in a direction which is opposite to the gradient of the loss function. Okay. So, this is one of the very important points of gradient descent algorithm, that if we want to reduce the loss, we should move in a direction which is opposite to the direction in which the gradient of the loss is. Okay. Now we will see after gradient descent how my weights are updated. So suppose we have the weights at a time t plus 1, then that is equal to Wt at the time t, the weights, minus eta gradient of L with respect to weights, that is my new weight. So at time t plus 1, if I see, I will have my previous iterations weights minus there is a factor eta, which we will look into what exactly it is to what it is called as, and what are the values that we should take for eta, and then we have the gradient of loss function. Okay. Similarly, for the change in biases also, this is the similar equation we can follow. And we are moving in a negative direction, so we have this minus term, negative to the gradient of the loss function. Okay. Now, if we put these two in a vector, W at the time t plus 1, the bias at the time t plus 1 equal to the weight at time t, the bias at time t, these are two vectors, minus eta into the gradient, okay, with respect to weights and biases at time Wt and Bt. Sorry, it should go up at time Wt, Bt. Okay. Now, my final equation is theta t plus 1 equal to theta t minus eta gradient of L, L theta, where what is my theta t plus 1? Theta t plus 1 is coming from here, which is weights at the time t plus 1 and biases at the time t plus 1. So, this entire thing is coming in theta t plus 1, whereas your theta t is nothing but this one, omega Wt and Bt, that is the weights and biases at the time step t. So, this is my theta t, and then eta, which is the learning rate, and then this vector is coming as gradient of L with L theta. Okay. So, this is the weight updation or the parameter updation equation in gradient descent algorithm. So, this is how the gradient descent algorithm works. Okay. Now, so if I want to show the algorithm, so we start at t equal to 0, maximum iterations we take it usually a very high value of 500 or 1000, and while t is less than this max iterations, keep doing updating the weights using these equations, and then when the number of iterations are reached, you come out. So, that is the algorithm, and usually we keep the number of iterations large value, so that we can continue this process of weight updation can continue till it converges. Okay. So, converging means it comes to the lowest point, it comes to the minimum error point. Okay. Now, we will come to something which is called as the learning rate in gradient descent. What is this learning rate? Now, we have seen this is the way the weights are updated. Wt t plus 1 at the time t plus 1 is equal to at the time t minus eta gradient of the loss function with respect to the weights. Now, this eta is called as the learning rate. Now, this eta can take any value. It can take 1, 2, 3, 0.1, 0.2, 0.3, any value. Only thing we have told that it cannot take a negative value. Okay. Now, suppose I have a loss function in the y-axis. Suppose weights are there in the x-axis, and we have we start at a random point in the in the curve, and we slowly we come down to a point. This is my point of convergence. This we called as the convergence point, which is the minimum point. Okay. This is my point of convergence. Now, if my learning rate is very small, what happens is we require a lot of steps before we reach to the minimum point. So, it takes a lot of time to come to the convergence. Suppose my learning rate is very high like this. Okay. So, we start from here and it goes in this, this learning rate is very high. Instead of coming like this, it drastically it goes here, then again from here it goes here, again it goes here. So, what happens is, in this case, if the learning rate is high, drastic updates may lead to oscillations and can never converge. So, it leads to oscillations. We can see that it is not coming to the point of convergence. So, if it is the point of convergence, it is never coming there. Okay. It is just oscillating. So, we miss the minima. Okay. And then this is something where we have an optimal learning rate, where it takes some value of eta which is not too small or not too large, and we get into the point of convergence or minima point very fast. Okay. So, basically this eta, the learning parameter, learning rate, is a hyperparameter in neural network that controls how quickly the model learns during the training. And usually eta values are chosen to be 0.01, 0.03, 0.1, 0.3, etc. Okay. Those are the usual default values that are chosen. Now, so we have learnt about, till now we have learnt about gradient descent, we have learnt about weight updations in gradient descent algorithm, how the weight updations happen, then what is the learning rate. Now, we will come to something called as the or some concept about convex and non-convex loss functions. Now, we will try to see what is a convex function, what is a non-convex function. Suppose we have a graph f(x) equal to x square and it looks like this. Now, if we take 2 points in the graph and we try to join them, what we see is a line connecting 2 points on the curve always lies above the curve. If you take any point, it will be above the curve. Okay. So, this type of curves or functions are called as convex function. Whereas, if we take a function like this, x is this one f(x) and it is like this, and you take 2 points and you join them, it is not always that it will be above the curve. So, these type of functions, they are called as non-convex functions. Now, if we see this non-convex function and if we compare with the convex function, this convex function is having only one minima point. Whereas, if we see here also it looks like a minima point, here also it looks like a minima point. Okay. So, there are multiple value in a non-convex function. Now, what happens if my loss function is of this type? Okay. If it is a convex function, very good, we have only one minimum point and we will try to reach there. But if my loss function is a non-convex function, what are the things that may come into picture? We will try to see. And here I have told that gradient descent converges to global minima in case of a convex function. We will look into what is a global minima, what is a local minima, and then again we will come back to this point. So, as I was telling, this is a non-convex loss function, and if you see, these are called the local minima because they are like a valley, but they are not the point where you get the minimum of the curve. So, wherever you are getting the minimum of the entire region, that is called as the global minima, and the other valley points we call as local minima. Similarly, this is the global maxima, and these in between the crests, they are called as a local maxima. So, this is very much possible when we have a landscape of non-convex loss function. So, for global minima, what mathematically how we can write it as, if x star is your point of global minima, then f of x star is less than f of x for all x belonging to R. Okay. So, it is minima over all possible values of f. If this is x, then all possible values of x, your f x star is the minimum. Now, what about local minima? How do I define it mathematically? So, if x star is my local minima, in that case f of x star is less than equal to f of x for all x minus x star mod, that means in a vicinity point which is less than delta, and if there exists a delta greater than 0. What does it mean? for all points close to x star, your f of x is greater than f of x star. Okay, so this is the concept of local minima. And for global minima, f of x star is much less than f of x for all values of x. Now, what happens here? Once again, I will come back to this local minima picture, and we will see there are two things that can happen here. When we have a non-convex loss function and we have this kind of a graph, then when we are coming down the valley, the algorithm may get stuck here, because this is also looks like a minima, and we know mathematically any minima at any minima point the gradient is 0. Okay. So, at this point in the local minima also the gradient will be 0, but this is not the global minima. That means there is more chance of the error getting reduced, but we are stuck here. Okay. Now, this is one thing that may come. Another thing is there is something called as the saddle point. Now, what is this saddle point? Saddle point means suppose you have a local minima and then you have a global minima, and you have something like this, and in one side of this it is going down, and in one side it is going up, and here it is like a straight kind of a region, flat kind of a region, where if you draw the gradient is 0, but it is not a local minima also. So, this is called as a saddle point. And what happens when if we get stuck in a place where the gradient is 0? What is the most important or what is the flip side of getting the gradient equal to 0 in this case? What is the disadvantage? Not flip side, disadvantage. So, at the saddle point the gradient is 0, but it is not a local minima, and what we see here is the weight updation, which is your weight in the next iteration, is equal to the weight in your present iteration minus eta into gradient of L. Now, if your gradient is 0, then this factor becomes 0, and then your weight updation Wt plus 1 is equal to Wt. That means your weight updation stops. That means your model stops learning. So, this is a problem which we might face when we are working with non-convex loss functions. For convex loss functions, it will always go into the point of convergence will be the local global minima, but in this case it can get stuck in local minima or at a saddle point. Okay. So, gradient descent may settle in a local minima or in a saddle point in case of non-convex function, loss function. Okay. Now, the question arises how to solve this problem if we are getting stuck in local minima or at a saddle point. This will be the topic of discussion in a subsequent lecture of mine. So, with this one I come to the end of today's session. We will quickly have a summarization of what all we have done today, what all we have discussed today. So, we started with what exactly optimization means. Optimization is the process of maximizing or minimizing any mathematical function that we got to know, and then what is the function of this, what is the reason why optimization is so important in machine learning or deep learning, because we always want the error or the loss from our model to get reduced. So, we want to minimize the loss from the error from the model, and the algorithm that we learned today is the gradient descent algorithm, which is the backbone of most all of the deep learning models, heavily deployed in deep learning. And then what we understood, what exactly is gradient descent trying to do? Gradient descent is trying to find out a structured way of movement in the weights and biases plane. That means weight updation and bias updation will happen in a structured way such that the loss after the loss from the network after the weight updation is reduced compared to your previous iteration. And this happens in an iterative way It is the first order iterative process because we take the first order gradient of the weights of the loss function with respect to the weights and biases. And we have seen what is partial derivative, how the gradient comes, how the entire mathematical formulation of gradient descent algorithm happens, and then we have seen how the weight updations happened. Wt plus 1 in the t plus 1th time is equal to Wt minus eta into gradient of L. Now that eta is called as the learning rate, and there are constraints if we choose learning rate to be very small. There are constraints if we choose learning rate to be very large. For very small learning rates, it takes a lot of time to converge to the minimum point, whereas if it is too high, then it drastically changes the weights, and what happens is it oscillates and we will miss the minimum point. It oscillates and it doesn't come to the minimum, it diverges. So in that case, we need to choose some learning rate which is optimal, okay, which is neither too high nor too low. And then we have spoken about convex and non-convex loss functions. How is the landscape of convex loss functions look like? What is the landscape of non-convex loss functions look like? What is the concept of global minima and local minima in case of non-convex loss functions? What is saddle point? And what happens when in case of optimization of non-convex loss functions? What happens when we get stuck in a local minima or a saddle point? Okay, so because the weight updation stops, so the learning of the model actually halts. So with this, I come to the conclusion of my today's session. I hope you all have understood the gradient descent algorithm, and in the next session I will be discussing about the back propagation, in which we do all these partial derivatives and take the partial derivative of loss functions. Whatever I have told in this session, we will look into how mathematically they are done. So we will have a full session on back propagation algorithm, and then in the subsequent sessions we will look into how to solve this problem of getting stuck in local minima or saddle point. So with that one, I conclude today's session. Happy learning to all of you till we meet in the next session. Thank you all.